Video 4-1, Properties of Light, Photoelectric Effect, and Quantum Theory. So, in Chapter 4, we're looking at the arrangement of the electrons in the atom. Okay, first thing we're going to look at actually is the properties of light. Okay, we can consider light to have the properties of a wave. Anything that has a wave has certain characteristics to it. One, first of all, is the wavelength. Okay, and this is the distance from what's known as either the crest, the highest part of a wave, to the next wave, next crest, or from the trough to the trough of the next wave, or from any corresponding spot on one wave to the corresponding spot on the next wave. So from the beginning of the up part to the beginning of the up part. All of these are all going to be exact same distances. Okay, wavelengths, we give them the symbol that looks like this. This is called lambda. Okay, now, if you were to have these waves moving and you stood at one spot and you counted how many waves passed the point in a given time. Okay, so in other words, if you were go down to the ocean, stand in the water and see how many crests, every time a crest went by you, that would mean one wave went by. How many waves passed you in a given point? This is known as the frequency of the wave. Okay, and we give it the symbol nu. These are all Greek symbols. Now, you may want to draw it like that. Okay. Now, do not draw it like this, because if you draw it like a V, we are going to be using V's. So make sure you know the difference between your V and your nu. Okay. So frequency is basically how many waves pass a point per second. Okay. The units are waves per second, or just 1/seconds, or seconds to the -1, which is the same as 1/seconds, or the units of hertz. So a wave that has a frequency of 1 hertz basically means it's 1 wave per second. Okay. Now, before 1900, light was thought to behave solely as a wave. Okay. Now, anything that is a wave, the energy associated with that wave is directly proportional to the amplitude, or how high the wave is. Okay. And if you think about ocean waves, the ones that are really big have a lot more energy to them compared to the ones that are pretty small. Okay. So for light, well, if you put more energy into it, what happens? Well, it gets brighter. Okay. Obviously, if you take a flashlight, the batteries get weak, it gets dimmer. Put in new batteries, it gets brighter. You're putting in more energy to it. So the energy must be the same as the amplitude, which is the same as the brightness. Okay. Now, we have this relationship here. C is equal to lambda times nu. Okay. You know this is the wavelength, and this is the frequency. C is the speed of light, 2.998 times 10 to the 8 meters per second. Okay. So for any light, okay, if the frequency changes, or the wavelength changes, the frequency has to change also. If one goes up, if the wavelength goes up, the frequency has to go down, because both of these have to equal a constant. Okay. So, what's the frequency of light if its wavelength is 3.56 times 10 to 3.45 times 10 to the 6 meters? Okay. Well, we use our formula and basic problem solving techniques again. Don't just plug numbers in, solve for the thing you're solving. Solve the equation for the variable that you want. So, frequency, C, you know, is 2.998 times 10 to the 8 meters per second. Okay, and rearrange the equation. So, frequency, divide both sides by lambda, must be equal to C over lambda. Okay, and when you plug those numbers in, 2.998 times 10 to the 8 meters over seconds, and then you're going to divide by 3.45 times 10 to the 6th meters. The units cancel out, and what you're going to be left with is just going to be 1/seconds, okay, which is what we expect. and you can do the rest of the math yourself. Okay. Now, light is a type of energy that's known as electromagnetic radiation. Okay. All forms of electromagnetic radiation travel at the same speed, which is the speed of light. Okay. So anything that is like light, also classified as electromagnetic radiation, travels at the speed of light. Okay. Now, what are the different types of electromagnetic radiation? Well, they all fit into what's called the electromagnetic spectrum, electromagnetic radiation spectrum. Okay. Visible light is a really, really small part of it. Okay. Now, if we arrange electromagnetic radiation by wavelengths, okay, as the wavelength gets shorter, the frequency gets higher. So if you notice high frequency, it's a short wavelength. If it's a low frequency, small number, it's a large wavelength. Okay. Now, lowest frequencies are your radio waves. Okay. As you start moving up in the spectrum, you run into things called microwaves. What's the difference between a radio wave and a microwave? Just the wavelength and the frequency. A little bit higher than that in terms of frequency is infrared. Okay. And notice the wavelengths are getting shorter and shorter. Visible light, which is basically light or electromagnetic radiation that your eyes are sensitive to, is a real tiny part of the spectrum. Okay. And visible light is broken up into a variety of colors. When you put these all together, you basically get white light. Okay. But remember Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. Okay. In order from low frequencies to high frequencies. Okay. Or long wavelengths down to, oops, can't see it, short wavelengths. Okay. Now, past violet is ultraviolet. Past that is X-rays and gamma rays. Okay. So, easy way to remember, where's ultraviolet? Well, it should be next to violet. Where's infrared? It's next to red. Okay. Now, in terms of energies, okay, the low frequencies will give you lower energies. The high frequencies will give you high energies. Okay. Now, we look at something called the photoelectric effect. Remember, scientists thought that light was a wave. Okay. Now, what is the photoelectric effect? Electrons can be emitted from a piece of metal when light shines on it. In other words, electrons get shot out and you get an electric current. Okay. So, shine some light on some metal, like sodium metal in a vacuum, and they found that electrons would be ejected from the surface. Okay. And they thought, well, it's kind of cool. Okay. But as they started playing with the different frequencies or colors of light, they found that only certain frequencies would cause it. Okay. And it didn't matter how bright they made the light, if they didn't have the right color, the right frequency, the photoelectric effect wouldn't work. Okay. So, what happens? Well, let's say they tried red light and they shot it at, instead of using sodium, they used potassium here. Okay. And nothing happened. No electrons were shot out. Okay. They tried green light and electrons were shot out. When they tried violet light, electrons were shot out. And the difference, they said, well, must be that red light is not bright enough. There's not enough energy to it. So what happens if we make it brighter? Well, the electron should be shot out. The problem was, if they made, no matter how bright they made the red light, they could not get an electron to be shot out of a piece of metal. The green light, they said, well, okay, that works. Well, if we give it more energy, it should come out faster. If they made it brighter, they didn't come out faster. They just had more electrons be shot out. Okay? Same thing with the violet light. If they made it dimmer, they did not get the electrons going slower. They just had less electrons. Okay? So, turns out that red light, no matter how bright they made it, it didn't have enough energy to eject electrons. But, so what's the significance of this? Remember, we said if light is a wave, the brightness is proportional to the energy. Okay? No matter how bright the red light is, no electrons would be ejected from this. Now, this basically is not what you'd expect from a wave. If you made it brighter, you give it more energy, the red light should get more energy, and it should work. Okay, so the energy of light was not proportional to the brightness, which means it doesn't have the properties of a wave, which is what's supposed to happen. Okay, energy of a wave must be proportional to its amplitude. So, what's the explanation? Well, a guy named Max Planck came along, and he said, well, turns out the energy of light is not proportional to the brightness. It's proportional to the frequency. Okay? H was known as a constant, Planck's constant. Okay? And the energy of the light is proportional to the frequency of the light, not the brightness. So no matter how bright or how dim you made it, as long as you don't change the frequency, the energy is always going to be the same. Okay? And also, for the photoelectric effect to work, there's a certain minimum energy known as a threshold energy to cause the photoelectric effect to take place. Okay. Then, our buddy here, Einstein, he came along again and basically said, well, what is light? Well, he said light is actually not a wave. It's actually a bunch of particles called photons. Okay? And the energy of each photon, each individual particle, is quantized. It has a definite amount of energy to it. And light is actually both a particle and a wave. And you say, wait, how can that happen? Okay? It's not that the particle is traveling up and down like this, like a wave. Okay? The particle, the photon, travels in a straight line. Okay? Now, where are the wave properties coming from? It comes from the fact that as your photon moves, it generates an electric field and a magnetic field around the photon. Okay, so think of this line as the path of the photon. As the photon is here, it generates an electric field that goes up above it and a magnetic field that is perpendicular 90 degrees to it. Okay. As it moves, as the photon moves to here, the field gets a lot bigger and a lot bigger. When the field moves to here, or when the photon moves to this point, it's getting smaller. At this point, the photon actually has no electric field or magnetic field. Then as it moves here, the field moves in the opposite direction. Now the electric field is down, and the magnetic field, instead of going to the right, is going to the left. Okay? So, as the photon moves in a perfectly straight line, the magnetic field oscillates up and down or left and right. Okay? And the electric field will be 90 degrees to it. So the wave comes from the fact that as the photon moves, the field oscillates and you get this nice little wave motion. Okay? And Einstein said the energy of light is actually calculating the energy of the photon and still uses Planck's equation, h times the frequency. Okay? So what does all this have to do with electrons, since that's what we're looking at in this chapter? Okay? Well, so far in the previous chapter we looked at the structure of atoms. We know where the nucleus is located, but we never figured out where the electrons are. Okay? And how are they actually arranged? How come the electrons don't collapse into the nucleus? Because the nucleus is positive and the electrons are negative. Okay? Well, a guy named Louis de Broglie came along, and he said, well, if light can behave like a particle, then a particle should be able to behave like a wave. In other words, waves can be particles and particles can be waves. Okay? So he said the frequency or the wavelength of anything that is moving, this is not new, this is velocity, is equal to h divided by the mass and the velocity. Okay, so an electron can behave like a wave. Okay, now, where's the electron? Okay, well, turns out, when we talk about quantum theory, okay, how do you figure out the location of a wave? Well, the wave is in one spot. Okay, and also, there's something called the Heisenberg uncertainty principle. Trying to locate an electron with a photon, in other words, if you want to see where it is, you need to shine light on it. But the process of shining light on it actually knocks the electron off course. Meaning, if you say, oh, look, there's the electron, actually it wasn't there. Because once you hit it with a photon, it moves it off its proper course. Okay? So Heisenberg basically said, well, it's impossible to determine simultaneously both the position and the velocity of an electron. Okay? So if you want to know what is the path of an object, you need to know where it is and what speed and direction it's going. And Heisenberg basically says that can't be done. Okay, so remember, we're trying to figure out where the electron is. Okay, well, what's the problem? Well, the Schrödinger wave equation comes along and says, well, we can mathematically describe the properties of an electron, but it doesn't tell you where it is. It gives you a three-dimensional area of high probability of finding an electron. Okay? And that's good enough because we don't really need to know where it is. We just need to know an area where it's probably going to be. It's just like if you're sitting around in class, okay, your parents want to know that, yes, you're in the classroom, but they don't really want to know exactly where you are. They just want to know that there's a high probability you're in that classroom area. Okay? And these areas of high probabilities are what we call orbitals. Okay? So we don't actually describe where the electron is, we actually describe electron orbitals. Okay? And these orbitals have a specific amount of energy. The electrons have to have this energy to be in those orbitals. And the review. Okay, which statement is correct? Make sure you read it carefully and pick the correct statement.